Hey everyone, today we're going to talk about 1's complement, 2's complement in binary. Whenever we're talking about 1's complement, we're dealing with negative numbers. Okay, so I have negative in binary. In order to convert using 1's complement, I take 2 in binary, or positive 2, so that becomes 0, 0, 1, 0. Then you invert the numbers. Zeros becomes 1, ones becomes zeros. So you have 1, 1, 0, 1. Okay, so this last bit over here, or the most significant bit, that tells you it's a negative number. So if I was to convert this back to my to a decimal, we will convert it to take the 1's complement of this, then convert it back. So that becomes 0, 0, 0, 1, 0, which gives you 2, and you apply the negative sign. Now, when we talk about 2's complement, it is 1's complement plus 1 added to it. So let's say that I want to take negative 5 in binary. Now to do that, first I have to put positive 5, so it's going to be 0, 1, 0, 1. Then I take the 1's complement of that. So 1, 0, 1, 0. Then I add 1 to it. So I get 0 plus 1 is 1. Yeah, 1. Then carry the 1 over. Carry the 0 and 1. So this is the 2's complement of negative 5. Okay. Now let's look at some other exercises. So delete this. I want to convert 1, 0, 1, 1, 0 using 2's complement. Signed, and then convert it to decimal. So first thing, we had to check if the most significant bit of here is negative. Is it 1? If it's 1, it's negative. So first we're gonna do the 1's complement. So we're gonna flip all the bits. So it's gonna be 0, 1, 0, 0, 1. Then we add 1 to it. So you get 1 plus 1 is 1, 0. Keep the 0, carry the 1, you get 1. You get 0, 1, and 0. So you get 0, 1, 0, 1, 0. Okay. Now, once we get this, we're going to have to convert this back to decimal. So this is the equivalent of 10 in base 10. So since this was negative over here, those, this becomes negative 10. Let's do another one. Use 1's complement of 11000 signed and decimal. Okay, we look at the most significant bits, it's 1, so the final answer has to be negative. But since 1's complement, all we do has to flip it. So it's going to be 0, 0, 1, 1, 1. So this is the equivalent of 7 in base 10. So, and since this is negative, so the answer is going to be negative 7. So far we have worked with either 2 bits, 3 bits, or 4 bits. What happens if it's 8 bit? Okay. So what I mean by 8 bit is you have 0, 0, 0, 0, 0, 0, 0, 0. That's 8 bits. So, and all your numbers is going to go over here. So let's use a problem. Let's say you want to use negative 8 in 1's complement. Eight bits. Okay. So first, do the positive 8. So you get 1000. That's in 4 bits for 8. Then add 4 more zeros after that. That will give you 8 bits. Since I want the 1's complement of it, I invert the numbers. It's going to be 1, 1, 1, 1, 0, 1, 1, 1, 1. So that's negative 8 in 1's complement in 8 bits. You could do the same thing. Let's say that you want to do negative 10. Actually, let's do negative 13 in 2's complement, 8 bit. Okay, first we had to put this in 8 bit, so 13 in 8 bits, which is going to be 0, 0, 0, 0, 1, 1, 0, 1. Then invert it, so 1, 1, 1, 1, 0, 0, 1, 0. Then add 1 to it. You get 1, 1, 0, 0, 1, 1. So that will give you negative 13 in 8 2 bits complement. How do I put floating point numbers using 32 bits? So what if I have negative 18 times 2 to the negative 8. So we know the most one has to be 1 because it's a negative number. So that's going to be 1. Then you have 8 bits of exponent and 23 bits of mantissa. So this is going to be okay. So let's say that you have to do this number. Negative 18 times 2 to the negative 8. So this will be in a floating point representation which has 32-bit numbers. The way the 32 bits is broken down is your one sign bit that goes between 0 or 1. Then you have 23 exponent bits, 8 exponent bits and 23 mantissa. So you start with your most significant bits. Since it's a negative number, you put 1. Now you want to have 8 exponent bit. So, and it says negative 8. You can convert that to positive 8. So it's going to be 1, 0, 0, 0. Since we are dealing with exponents, we kind of take the ones complement of the zeros. So that's 4, and you add 4 more ones. 1, 2, 3, 4. Then you have 23 mantissa. Okay, that means 23 zeros or ones. 18 has a value of 10010. Okay, that's 2, 3, 4, 5. Okay, then we have to put 18 more zeros in there because there's not been accounted those numbers, but it's part of the 30-bit. So it's going to be what, 13, 4, 18 more. So 0, 0, 2, 4, 6, 8, 10, 12, 14, 16, 18. That's how you represent negative 18 times 2 to the negative 8 in 30-bit numbers. I hope this helped you guys understand it.